right? I thought there'd be data. Is anyone out there?
Oh, okay. Let me bring up, how's the homework going? Are there any ones that anyone wants to talk about? You know, I never checked 2C, so maybe they don't come out comparable. Let's see. Okay, so that's really sloppy, but in 2C, we have x1 through xn, a random sample from the uniform 0 theta distribution, and in part A, you're to make an unbiased estimator based on x bar, and in part B, an unbiased estimator based on the maximum. So, kind of hard to do C without doing A and B, but I could do like let's look at the variance of both of these. So neither of these on their own are going to be an unbiased estimator for theta. Like the expected value, all right, x bar, the expected value of the uniform distribution is right in the center because it's got equal weight everywhere and it's kind of this balancing point. So you might see it in the table as alpha plus beta over 2, and the way I gave it in the table is alpha is the left endpoint of the interval and beta is the length of the interval. And so the expected value of x bar is always the same as the expected value of any one of them. And for this uniform distribution, that is theta over 2. So you can very easily turn that into theta by multiplying x bar by 2. That's your answer to part A. And then, so for part B, you would need to find the expected value of the maximum. And I'm going to need the distribution of the maximum in order to do the variance in part C. So I guess I should look at this. So to get the distribution for the maximum, I'm going to need the distribution for any one of them, the CDF, I mean. And so the distribution, the PDF is 0 off of the interval from 0 to theta. And then if the total area under what's supposed to be a straight line, a flat line there, if the total area is 1, this has to be at a height 1 over theta. So if you pick any x between 0 and theta, then the probability of being less than or equal to x is given by this area x over theta. So this is equal to 0, x over theta, or 1. It's going to be x over theta for any x between 0 and theta. It's going to be 1 for x greater than or equal to theta, and 0 for x less than or equal to 0. It's actually continuous at those two endpoints, so it doesn't matter that I have equals everywhere. Okay, so we know that the CDF for the maximum, this is the probability that the max of x1 through xn is less than or equal to x, and if you draw your number line thingy, this means that they're all less than or equal to x. So this is the probability. x1 is less than or equal to x, xn less than or equal to x, and because they're IID, you can factor these and it's all the same probability, so we get x1 less than or equal to x to the nth power, and this is x over theta to the n, and this holds for any x between 0 and theta. And the max and min always live on the same space as the original distribution, so this CDF is 0 if the x you're plugging in is below 0, and it's 1 if the x you're plugging in is above theta. So we know from this that the PDF for the maximum is the derivative of the CDF. And if you go ahead and split this out to x to the n and then 1 over theta to the n, you can just leave 1 over theta to the n sitting out front here, and then take the derivative of x to the n. So you'll get n x to the n minus 1, put an n up here, n x to the n minus 1. And this lives on the interval 0 to theta. You can close the endpoints or open the endpoints. It doesn't matter because it's a continuous distribution and there's no area under the curve at those points. Okay, so we need to find the variance. So I'm not sure what your answer to B is, but your answer to B is something like, so you're going to have found the expected value of this maximum, which means you actually have to do this part. So I won't complete this, but in B, the expected value of the maximum is going to be the integral from 0 to theta of x times n over theta to the n, x to the n minus 1 dx. And you're going to get something that's almost theta. It's going to have a coefficient that you can move to the other side to get your unbiased estimator. So then, now we can talk about part C. So in C, we want to look at the variance of our first unbiased estimator, which is 2x bar. And this is 4 times the variance of x bar because I pulled out that constant and it came out squared. And we know for any distribution, the variance for the variance for x bar is the variance for one of them over n. And if you look in the table, the variance for one of them, when you're talking about an alpha, when you're talking about a uniform on alpha to alpha plus beta, the variance is beta squared over 12, which is weird looking, but true. You can work it out and you'll get that. So the beta here is theta. So this is 4 theta squared over 12 over n, which is theta squared over 3n. So the variance for the other estimator, so there's some constant. Actually, there's 1 over some constant. And then the maximum. You would pull out that 1 over that constant squared, the variance for the maximum. And then this guy is 1 over some constant squared. And this variance is the expected value of the maximum squared minus the expected value of maximum all squared. And we already worked out that expectation. It was the constant times theta. And you can work this one out pretty easily because it's just scrolling. It's just this integral again, but you're putting an x squared here, and it's just another simple power integral. You know, you combine the x's and you integrate with respect to x. So this guy over here ends up squared. And this guy here should be something times theta squared. This is going to be like another constant. That's a constant. Theta squared, where this is some other constant. And so if you put this all together, you get that some constant minus this guy squared times theta squared. So it's going to come down to comparing, and then stop me if this was the problem, comparing this to 1 over 3n to figure out which one has the smaller variance. So they should both end up with a theta squared and then some kind of constant in front. And so you want to say that hopefully one is less than or equal to the other for all n. They should have the same value just as a check when n is 1, because when n is 1, x bar is just x1 and the maximum is just x1. That'd be a good, check. Okay, so hopefully that makes sense, and I didn't actually by-step the actual question, which is maybe you got this and it didn't simplify nicely. I think it should simplify okay. Yeah, which estimator is better in terms of variance? So one of them is going to be better, and that one is going to have lower variance. And the variance is a function of theta, so you're going to get to something like comparing Now I'm totally making this up, but like 1 over 3n theta squared to n minus 1 over n theta squared. Now this is just made up. That is not what you get. But then it comes down to comparing but it comes down to comparing these coefficients as a function of n. I'll ask if there's more questions about the homework, but this kind of brings me to a point that's coming. So if we're estimating a theta, forget this problem. This is not this problem. And we have two unbiased estimators. If we compute so these are unbiased. If we compute the variances, then we would like the one with lower variance. But the variances, these guys depend on theta, and theta is unknown to us. So if you don't know theta, how do you know which variance is lower? So it might be something obvious like a 1 over 3n theta squared versus 1 over 3n plus 1 theta squared. That's just an example where you can say one is lower than the other without knowing theta. But it could be, and I am totally making this picture up. So if you graph these as a function of theta, that the variance of one estimator, so you're graphing the variances here, looks like this. So this is a graph of the variance of theta 1 hat, and you can see I've made it some kind of function of theta. And if you have another estimator that looks like this in its variance, so the variance of some theta 2 hat, now I can't say that one estimator is better than the other because this was really a time to use color. This in. Because in this picture, it appears that the second estimator is better, has smaller variance up to this value of theta. And then the first estimator seems better in that it has smaller variance after that. So you can't say that one is better. But what if you could find an unbiased estimator that has uniformly smallest variance? And uniformly in math means like for all. So the UMVU coming up is going to be something that is below every possible variance function you could draw. So it corresponds to another unbiased estimator, but you can guarantee it's below, the variance as a function of theta is below any other variance of any other unbiased estimator in all the land. The UMVU is coming. Let's get back to convergence and distribution. So convergence and distribution was our second type of convergence for sequence of random variables, and it was just convergence of CDFs. So we were talking about the idea of convergence in distribution. And we write that a sequence of random variables converges in distribution to X. We put an arrow and some kind of D over it. And I gave you several other notations, and if you want to use one of them, that's fine. But I'm using a lowercase d for reasons. Okay, so this means that the limit as n goes to infinity of fn of x is equal to f of x, where the fn is the CDF of xn, and f of x is the CDF of x, and this limit has to hold for all points of continuity of f. So we did an example last time where I took a random sample from a Pareto distribution, and we looked at a new sequence of random variables where we took the minimum, which does depend on n, and that minimum is shrinking, shrinking, shrinking as n gets large, right? If you sample from any distribution that lives on 0 to infinity, the minimum is probably somewhere down here. And as you increase the sample size and throw more things in, the minimum just has a potential to get lower and lower and lower. And if I have an infinite number of those x's, the minimum is going to totally squish up towards 0. So what we looked at last time was the sequence of random variables yn that I defined to be n times the minimum. So this is going to 0 in just kind of an intuitive sense, like not a real sense. I mean, yeah, also a real sense, but that's not the point I want to make. And this is blowing up. And so last time we saw that if x1 through xn are IID Pareto with parameter gamma, we saw that this yn, which was n times the minimum, is converging in distribution to the exponential distribution with rate, I squished that in the corner, gamma. So the n blowing up was kind of enough to balance out the minimum going way down to 0. And we did that last time, and this time I wanted to do a new example, which is what happens if that n is gone. So, right there. So here is a new example. Suppose that I have x1, x2 through xn, and these guys are IID from, again, the Pareto distribution with parameter gamma. And let's investigate the convergence in distribution of just the minimum. You don't have to name it yn, but I will. The notation I've chosen for the minimum doesn't really show the dependence on n, but we know it depends on n. So first thing we do is write out the CDF for yn, and I think we've done all this work, so I will maybe blow through this. I don't know. The CDF for yn, and by all means you can write f sub yn. It's just a lot of subscripts. As long as you define this to be the CDF for yn, then yeah, go for it. This is the CDF of the minimum evaluated at y. And this is by IID-ness and the conversation that we've had every time when we look at a minimum and flip it around. This is 1 minus the probability that any one of them is greater than y to the n. And yeah, and this is a Pareto distribution. So we wrote down the CDF last time, and now I'm going to use 1 minus that CDF, which is 1 over 1 plus y to the gamma to the n. So I'm rushing a little bit, like not writing out the CDF. So the CDF for the Pareto is 1 minus 1 over 1 plus x to the gamma. And I just used 1 minus that, and I used y instead of x. Okay. Okay, so this is 1 minus 1 over 1 plus y. What am I don't even need to rewrite this. Sorry about that. Let me actually make this a little more concise by saying, I'm going to have to erase that CDF on the side. Sorry about that. So this holds for y greater than or equal to 0. And the CDF is 0 for y less than or equal to 0. It's actually continuous at 0. So I get to put the less than or equal to and the greater than or equal to. And the reason I bothered to write that is because if you let n go to infinity, and I'm going to do that on this piecewise thing, so the bottom stays at 0, and the top, well, if y is strictly positive, strictly positive, then this guy is greater than 1. And so this thing is a positive number that's less than 1. And when you raise that to the n, this whole thing is going to 0. So I get, actually I'm going to have 3 things in the brackets down here. I get 1 if, no, I didn't write if below, so let me not write that here. If y is strictly greater than 0. But if you plug in y equals 0 to this, then you get 1 minus 1 to the n, which is for finite n, 1 minus 1. So you get 0, which actually isn't changing in the limit. I guess I didn't well motivate why I looked at this part. And the reason I looked at this part is because, so you're just going along doing this kind of by routine, and you get down to just kind of a constant, something that doesn't look like a CDF. And that's where you have to consider what happened for the rest of the space. This equals, this is a horrible equals. I'm going to graph this. That doesn't equal that. If I graph this result in y, then this is 0 all the way up to and including y equals 0. And then it jumps up to 1 at 0 with a hole there. And that is not a proper CDF. CDFs have to be right continuous so that they can be interpreted as the probability they are. Because if you are taking a value and saying the CDF has to give me the probability I'm below that value, then this random variable takes on only non-negative values, so I should get 0, 0, 0, 0, 0. And actually, I should pop up to 1 right here. All the probability is focused on 0. And it doesn't make sense to pop up sort of just after 1. You have to pop up on numbers, which makes this a right continuous thing for this to make any sense. But our limiting CDF, so the point is that this is not a CDF because it's not right continuous. However, please forgive my drawings, it is equal to this guy, open, closed. Let me make that more clear, open. It is equal to this guy, open here, and closed here at all points of continuity. Like I'm trying to say, if it's messed up at a discontinuous point, then you can just make it right. That function, those 2 functions match every place where these functions are continuous. And this guy is a valid CDF. It's now right continuous and is a valid CDF. And so this equals, this is such bad math, equals this picture, equals this phrase, but this equals the CDF of the random variable x that is equal to 0 with probability 1. And that's it, nothing else. So it's a constant. In other words, x is just 0, but probabilistically we say it's 0 with probability 1. So to finish this off, the yn, which is the minimum of our Paretos, is converging in distribution to x, where x equals 0 with probability 1. And a sloppier way to say that would be the minimum x converges in distribution to 1. But our convergence in distribution was only defined for random variables to random variables. So the 1 on the right side of the arrow is something that's random but equal to 1 with all of its probability. And this is what we expected out of the minimum, because the minimum keeps going down towards 0. And so the limiting distribution is this distribution that has all of its probability right on 0. All right. Okay, so let's prove some things. I said last time that convergence in probability was stronger than convergence in distribution. So I've got a theorem for you that states that more formally. And that is, if xn converges in probability to x, this implies that xn converges in distribution to x. So to prove this, I'm going to let fn be the CDF for xn. I'm going to let f be the CDF for x. I'm going to take an epsilon greater than 0 because I'm going to need that for the convergence and probability part. And I'm going to let x, little x, be a point of continuity of the capital F. This is just all the setup notation I need. Okay, so check this out. Fn of x, like a bullet. We'll have 2 bullets and they'll prove what we want. This is, by definition, the probability that xn is less than or equal to x. That's just how that CDF is defined. So I'm going to drag in the other random variable x. I'm going to write this as the probability that xn is less than or equal to x, comma, and x is less than or equal to x plus epsilon, plus the rest of the probability, so xn less than or equal to x, and x greater than x plus epsilon. Those are disjoint events, and together they make up the original event that we care about. So I'm going inside the probability. This event, if you look at a number line with an x and then an x plus epsilon, this is saying that xn is somewhere down here and x is somewhere up here. And this implies that the distance between xn and x must be greater than epsilon. But that's not an if and only if. You know, if you move totally far away from that point x, go somewhere else on the number line, you can have your xn minus x be greater than epsilon apart without having xn less than x and x greater than epsilon plus x. So this guy as an event is a subset of this guy. Like if this happens, this must happen. But if this happens, this didn't necessarily happen. So right now I'm going to erase this because I don't have a lot of space, but I've got like an A contained in B, and that means that the probability of A is less than or equal to the probability of B. So if you want to write that out, you can say let A be the event that xn is less than or equal to x and x is greater than x plus epsilon. Let B be the event that absolute xn minus x is greater than epsilon. Then A is contained in B, and my point is that we get a higher probability if we rewrite it with the absolute value thing. So first term is just going to stay here. And then this is going to become probability xn minus x is greater than epsilon. Any questions? I could have done this all in one line, but I wanted to make sure you can find where the inequalities came from. I can make this even larger by, so in this first intersecting probability, two things have to happen. And any one of those things happening alone would have a higher probability, a greater chance of happening. So this guy, that probability there is less than or equal to the probability that x is less than or equal to x plus epsilon. So I am just dropping the xn less than or equal to x, which will give me something larger because in the top line, that first probability out of the two in the sum has more restrictions. So it's less likely, and I get this guy. And so just to finish off this bullet, this first thing is capital F, which was the CDF for x, evaluated at x plus epsilon, plus the probability, absolute xn minus x is greater than epsilon. And so I have a second bullet, and basically we're going to bound this fnx between two things, some of which we know are going to 0, some of which are kind of the limit we care to get. So I'm going to do the other bullet at higher speed. So on the other hand, that's what I mean when I write OTOH. On the other hand, if we look at F, the CDF for X, evaluated at X minus epsilon, and we do the same sort of thing. So this is X less than or equal to X minus epsilon. Oops, sorry, page is floating. This is X less than or equal to X minus epsilon and Xn less than or equal to X plus, and the other probability, I'm going to let Xn be greater than X. So going extra fast here, the last probability, I've got like an X and an X minus epsilon. And so if X is below X minus epsilon, and if Xn is above X, then that means they're greater than epsilon apart. But this is just one way that can happen. They could both be above X and yet greater than epsilon apart. They could both be below X. So many things could happen. So this guy is less than or equal to the probability of the same thing we saw before, that the distance between Xn and X is greater than epsilon. And then this guy, I'm going to drop one of them to get a larger probability. So overall, I've got this is less than or equal to the probability Xn is less than or equal to X, plus the probability that absolute Xn minus X is greater than epsilon. So I know I did that fast, but it's really the same, all the same stuff we did in the first bullet. So I'm going to take these bullets and put them together. So we have, oh, by the way, sorry, one more line up here. This is fnx plus this probability that xn minus x is greater than epsilon. Okay, so now I'm going to put them together and I'm going to sandwich the fn. So I have fnx is greater than or equal to fx minus epsilon minus the probability absolute xn minus x is greater than epsilon and less than or equal to, sorry, I have to scroll back, I forgot, fx plus epsilon plus the probability absolute xn minus x is greater than epsilon. So if we let n go to infinity all the way across, like this probability here, this first absolute value probability is going to go to 0 as n goes to infinity, since we assumed that xn goes in probability to x. The same thing with this last term over here. It's the same exact term. And so if you let n go off to infinity, On the left side of this big inequality, we get f x minus epsilon. In between, we get, I'm going to write this limit, but this doesn't really make sense. So I'm trying to take the limit as n goes to infinity all the way across here. And let me just finish writing this and I'll tell you why. I don't know that this limit exists. So all the fn's are, as n goes to infinity, for all n, are bouncing between these two numbers. That doesn't tell me that this actually has a limit. So I really should write like a lim inf, or a lim, I should do it with a lim inf and a lim sup, but I don't really want to go there. So the question mark means that circled limit may not exist. However, if we let epsilon, which is an arbitrary non-negative number, if we let epsilon go down to 0, it will get squished. It will be squozen. We will use a squeeze type theorem, and we'll get f of x is less than or equal to, and over here we'll get f of x, and those are the same, and that will force the limit in between to actually make sense. You know what? Ignore what I said about that limit maybe not existing. You have to think about it, but I don't want you to lose the rest of the theorem for that detail. And this means that the limit as n goes to infinity of f and x is, oh, here's where, by the way, I just used the fact that x was a point of continuity of f. Because letting epsilon go down to 0, this shouldn't go to f of x unless it was continuous at x. So that's kind of important. So I used that x is a, why do I make parentheses when they're not even going to hold? A point of continuity of f. And so we've got our conclusion, blah, blah, blah. And this implies that xn converges in distribution to x. Yay, us. Yay, us. Is there anything I can clear up in that proof? Aside from maybe the second bullet, because you'll get it if you know the first bullet. You just have to reason your way through the second one. Awesome. So this theorem was saying that if we have convergence in probability, then we have convergence in distribution, but it's not an if and only if. So just kind of as a note, in general, if xn converges in distribution to x, this does not imply that xn converges in probability to x. We already had an example of this, but I want to make it even simpler. And that example was the silly example when I talked about all the xn's having the same normal distribution that didn't depend on n, and x as well having the same normal distribution that didn't depend on n. That would serve as a counterexample here, but I just wanted to make a simpler one. So I'm going to do the same sort of thing. I'm going to suppose that x and then x1, x2, so I just kind of separate it out so you can see that it's just part of the list, that these are all IID with a distribution taking values -1 and 1 with probability 1/2 each. So they're all discrete, they all take on 2 values, they're all independent, they all take on the same 2 values with the same probabilities. So then, just like we talked about with the normal example, the fn of x, this is the probability xn is less than or equal to x, and we can write that out as a step function. It's going to be 0, and I don't really care though. It's going to be 0 up until we hit -1, then it's going to jump up by 1/2, then it's going to stay at 1/2 until we hit +1, and it's going to jump all the way up to 1. And it's going to be exactly the same as the CDF for x. So I don't even need to write that down because the xn and the x have the same distribution. So this is f of x. This holds for all n. So the limit as n goes to infinity of f and x is the limit as n goes to infinity of f of x, which is f of x. So we have that xn converges in distribution to x. But this was supposed to be an example of us not having convergence in probability. So I need to exhibit an epsilon for which one of the two convergence and probability statements does not hold. Check this out. However, the probability that absolute xn minus x is, say, greater than or equal to 2. This is actually the probability that absolute xn minus x is equal to 2, because the only way these guys that take on the values minus 1 and 1 in absolute value, that difference could be greater than or equal to 2, means that it must equal 2. And so this means that we can have xn equals 1 and x equals -1, or the other way around, xn equals -1 and comma, and x equals 1. And that or is a union, and those are disjoint events. Guys are disjoint. You can't have xn equaling 1 and x equaling -1, and at the same time having x equal +1. And so this is the probability xn equals 1 and x equals -1, plus the other guy, the probability xn is -1 and x equals 1. Oh man, Zuli is really mad at me. I brought her because she's one of the friendliest ones. My favorite, I breed a species that just came off the endangered species list. I've been breeding for a long time. They're called monkey tail skinks. They are so cool. I'll have to bring one, but they look like claymation dinosaurs, and they kind of move like old claymation stuff, but they have really intense claws. So even if they're being like friendly, I bleed a lot just handling them. Okay, so to finish this off, these guys are independent, so you get probability times probability plus probability times probability. So that's by independence. And then all of these probabilities are 1/2, 1/2, 1/2, 1/2. This whole thing is 1/2. And I started with the probability that the distance is greater than a particular epsilon. And that needs to be going to 0, but this is not going anywhere. This does not go to 0 as n goes to infinity. So we exhibited, right, for the counterexample, we need to exhibit a particular epsilon where this won't work. So xn does not converge in probability to x. So we have a counterexample. Sorry, I said because I looked at my clock. With epsilon equals 2.
Can we say something more general, like if if x is independent with all of them and multi-valued, that will never converge in probability? Because even though these have, let's say the idea I'm seeing here is like, even though they have the same distribution, they're not really coupled. They don't relate to each other.
Yeah. Yes, I think we can.
I
Yeah,
guess maybe we need
independence.
something.
I think independence is going to be enough. Let me write that down. Think about that because I'm out of time. Yeah, let me just double check before saying yes. So, I guess I do. I'm looking at the wrong clock. Still, I'm going to leave that as a note. I just want to state one thing for you, and that is something that I think you're going to find really useful. So that is that if xn converges in distribution to a constant, so C is a constant, that actually does imply convergence in probability to a constant. C is a constant. This is really easy to show, but I'm out of time, but it's going to be a much shorter proof than either of the two we just did, or one we just did, or I don't know what we did. But it's going to be a short proof, and it's going to be one I think you care about because we want to be showing that estimators are converging to constants. And a lot of the time showing convergence in distribution is easier than showing convergence in probability, but because this is constant, we can show convergence in distribution and it will imply convergence in probability. So constants are special. And next time, the central limit theorem is like big in statistics. Okay, so I'm out of time. And yeah, I guess I'm going to stay here for my office hour. So thank you and goodbye. If anyone wants to stick around, I'll be right here.